This will be part one of two on our discussion of coastlines. So, in this first part, we'll talk about what a coastline is, how it's shaped, how it forms, and then we'll talk a little bit about waves and how they erode the coastline. In the second part, we'll talk about the depositional processes that we see, how waves kind of deposit and move and transport sediment and coastal cells, and a few other things. So, let's get to it. First of all, what is the coast? Well, the coast starts at the shoreline. That's where the ocean meets the land. And we could think of right next to that shoreline, we have the near shore, which is the part that's underwater, and the foreshore, which is the part that's dry. And then as we move away from that, we get the back shore and the offshore. So altogether, those are the four parts that make up the coastal zone. So coasts are shaped by physical processes of erosion and deposition. And we're going to really focus on what waves do, but we're going to begin by talking about a little bit about like where do coastlines come from and kind of the big picture of what shapes them. And one of the first things that we have in that category would be changing sea level. Sea level can rise and fall, and there are two ways that this is experienced. So the first thing we want to mention is the global experience of sea level change. This is also called eustatic change. This is what happens to sea level worldwide. One of the things that is going to cause sea level to change would be the amount of water in the ocean. So this is affected primarily by the formation and melting of ice on land. So if you make a big mass of ice on land, that's not in the water, and so that would cause sea level to fall. The ice cap on the Arctic Ocean, on the other hand, because that ice is floating in the water, that ice actually displaces a volume of water equal to its mass. So melting or freezing the ice cap on the Arctic Ocean does not affect sea level. On the other hand, the southern continent, Antarctica, that ice is sitting up on land, and therefore it does affect sea level, as does the ice cap on Greenland and any glaciers that we see on land. That is basically water stored on land, and that would tend to lower sea level. As that melts, sea level globally will rise because there's more water in the ocean. A couple of items that are a little trickier to understand. One of them is the volume of the Earth's ocean basins. It turns out that plate tectonics has an effect on this, and we're not going to get into that very deeply because it doesn't really come into play in what we're talking about in the class. So, but you should just know that the volume of the Earth's ocean basins can change based on tectonic activity. And then the third item we have here is the temperature of the water. When the ocean water warms up, it expands and it takes up more room. When it cools down, it contracts and it takes up less space. So the changing temperature of the ocean water can cause sea level to rise or fall. The other way that we can look at sea level is what's happening locally. It turns out, even if it's rising or falling globally, there are some local effects that can cause it to rise or fall, either in tandem with what's happening globally or the opposite of what's happening globally. So local coastlines can rise and fall. We'll take a look at a few pictures of those in just a minute. And this happens due to tectonic and isostatic factors primarily. Also, it should be mentioned that in the short term, sea level can change due to things like storm surge, sea tsunamis, the tides. Those short-term changes are usually over the course of a few hours or days. And in some cases, like the wind-driven currents, El Nino and La Nina, that could be over the course of several months. But that's what short term is. It's not permanent. The long term changes are permanent trends and permanent changes. So let's take a look at the effect of sea level rise. Since the end of the last ice age, there has been more water going into the oceans. The planet's been warming up, so sea level is getting higher because the water is getting warmer and we're having more water in the ocean. And this has caused a number of coastlines to become what we call drowned. So sea level rises up and it floods valleys that were eroded by rivers, valleys that were eroded by glaciers and other types of erosional processes. And so these drowned coastlines, you can see the east coast of the United States. On the left-hand photo, you can see Sydney Harbor in Australia on the right-hand photo. Those are both examples of places that had been extensively eroded by rivers and then flooded by rising sea level. However, even though globally sea level is rising, in some places the local sea level is actually falling. This is an example from the west coast of the United States. Much of the California coast, it turns out, is rising because of plate tectonics. There is a convergent and a transform margin along the west coast of the United States. And so that tectonic activity can push the plate up in the air. And what happens in that case is you can see some stair steps. There's something there labeled a wave cut platform that we will learn how that forms in the second, in a little bit in this slide presentation. We'll talk about how that forms. But what you should know at this point is those flat areas used to be underwater. So if you look off the coast here, the waves are basically eroding what we call a wave cut platform because this section of the coastline is being pushed up, that old wave cut platform, and there's another one over here. Each one of those long stair steps is an old part of a wave cut platform that used to be under the water. Anyway, try not to get too confusing there. So some other things that can give us coastline, one of those would be volcanic activity. You can see the lava here in the two craters on the right-hand side are basically creating brand new coastline that then can be acted upon by the waves. And here's an example of the Mississippi River Delta. This is also creating some new coastline. It has kind of an interesting effect. All that extra sediment gives us new land, but at the same time, it weighs down the plate around that area, and that part of the tectonic plate actually sinks down a little bit due to the weight of all that extra sediment. So a river delivering sediment to the coast actually has a couple of effects that in some ways offset each other. So it's adding new material, but it's also causing the area to sink down. So let's take a look at the agents of erosion. So what actually shapes this coastline once it's present. So the primary agent of erosion, of course, is going to be waves in the water. The waves, what most people think of immediately would be the water pressure. A wave hits you, it can knock you over. A big wave has a lot of pressure, so it can move things around a lot. But water itself is not very hard, and therefore it's difficult for water all by itself to do a lot of physical damage. But the water has the ability to pick up pieces of sediment and then knock those pieces of sediment, which could be rocks or sand, into other rocks or sand. And that's what abrasion with sediment in the water is referring to. So a combination of water pressure plus the sediment in the water are what does a lot of the erosional work. In addition, you might recall a few chapters ago, we talked about water chemistry. And so the water can chemically attack the rocks and materials that are along the shoreline. Um, some of the minerals and rocks can physically dissolve. And then there are other types of chemical actions that the water facilitates that can cause rocks to break apart as well. And then this last item, gravity, you'll understand a little bit better if we just go on to the next slide. We can see where the water is most active. It's going to be most active right near the water line. And the reason for this goes back to the previous chapters where we learned about waves. And you'll remember waves can only work to a depth of about 1/2 the wavelength. So once you get deeper than that, the motion of the water is minimal, and therefore you don't have a lot of action there. If you look at the top part of this drawing, of course, there's no water there, there's air, and so the waves can't act there. And so the wave action is actually very much focused near the water line. This results in the creation of what we call a wave cut notch, which you'll see kind of on the right-hand side of that diagram, and a wave cut platform. So because the waves can't work too deep in the water, they will make a sort of a level surface offshore. You'll also notice that that cliff is being undermined, and that's when gravity comes into play. The waves cannot work the top part of the sea cliff, but they can dig away the material that's underneath, and eventually gravity will pull that sea cliff down, and then the waves can start to pick up those rocks and move them around. The waves are not perfect. They don't do a perfect job of cleaning off that wave cut platform. And so rocks that might be a little more resistant to erosion, or if the waves are moving in a certain way that doesn't attack some pieces of rock, you can get some what we call sea stacks, or some remnants of the original material sticking up above the water, standing up on top of the wave cut platform. And there in the sunset picture here, you can see that quite well. In the picture on the left, you can see kind of around the corner there, you can see part of the wave cut platform. But I think the sunset picture is a little bit better. You can see the platform there in front of the cliff, and you can see all the sea stacks sticking up above. And so that concludes our discussion of wave erosion. What we'll do in the next slide set is we will discuss wave deposition, and we'll discuss beaches and the transportation of sediment along the coastline, some features called barrier islands, and some other ways that sediment moves, including coastal cells. So that'll be the next slide set.